All right, what's going on, my fellow physicists? Today I'm going to be talking about the basic locomotion of Actinopterygii. So, what is Actinopterygii? Actinopterygii is a class of fish, and it is the class of ray-finned fish, which are fish that utilize thin, flexible, so-called rays, also called Lepidotrychia, within their fins to help support their movement. Largest class of fishes, making up approximately 99% of all fish species, which is that's pretty crazy. Also, this class approximately makes up 50% of the world's known vertebrate species. That is even more crazy to me. Extremely diverse class. There is always an exception to what fits into the class. So first, we need to understand water. Water is 50 times more viscous than air is. Think of viscosity as resistance to flow. The resistance to flow is caused by two major factors: hydrogen bonds and temperature. When hydrogen bonds are formed in the water gains more resistance to flow due to the bonds making it harder for water molecules to freely move within the water. Temperature, on the other hand, directly impacts the amount of bonds within the water. More bonds are present in colder water, and more bonds are broken in warmer water. Now I'm going to be talking about viscous drag and pressure drag. So, a drag force is a force that acts against motion. When fish swim, there is friction between the animal and the water. This friction is called viscous drag. So think about friction, like water coming up against the fish, right? So there is friction, the water hitting the fish, the two surfaces of the fish and the water. There is friction between those two surfaces. Um, so the friction between the animal and the water, this friction is called viscous drag. The more drastic change of shape an object has, such as jagged edges or less gradual changes of shape, the more of a turbulent wake and gap that will be left behind the object. And in this wake is lower pressure. So we can see here in my really bad drawings that I created, you could see that these shapes, just think of them as swimming. They're swimming through the water here, right? So we have the rectangle swimming to the left, um, and we can see that the water is having trouble smoothly going over the rectangle. You could see it's kind of hitting this corner here. And then when it finally does actually go behind the rectangle, it does create this kind of turbulence, this little gap behind it. And you can see the same thing with the sphere. Um, and the issue with that gap is that there is actually lower pressure. There's lower pressure behind the object than there is in front of it. There's higher pressure in front of the object, and there is lower pressure behind the object. So let's see here. This force causes resistance. The lower pressure and then the higher pressure here, it causes resistance. We can see that different shapes generate more or less drag. The streamlined slash fusiform body shapes grant fish speed and less energy usage. So here you can see this is the kind of like the optimal shape. And it's optimal because you can see there is little to no turbulence being created. There is little to no gap behind the object um, when the water passes by the object, or when the object cuts through the water. And this helps with the lower pressure behind the fish, or the object in this case, not be as present as it would be here with these more jagged or more defined shapes, not gradually defined, but bluntly defined. So now we're going to talk about fins. Though caudal fin shape varies heavily within ray fin fish, the most common shape is homocircle. And a homocircle caudal fin has its own shapes, such as a truncate and forked shape. Homocircle caudal fins primarily create thrust, and we know this because of the external symmetry they display. Whereas some caudal fin shapes, such as the heterocircle actually have an elongated bottom half or top half. And what this actually does is it grants the fish aid in water column buoyancy. So, for instance, if they had a longer bottom half, it would actually help the fish. It would grant the fish lift, right? Because it'd be pushing up. It's not. If you look here at the truncate and forked fins, they are symmetrical externally, so you can see. It's not gonna make. It can't make the fish go up or down. It is literally just propelling them forward. And that is because the top and the bottom are equal. Let's see here. So, the other type of caudal fin shape I was talking about, the heterocircle, is more common in older species of ray finned fish, such as sharks that lack a swim bladder, and it also can be common in paddlefish as well. Dorsal fins aid fish in staying balanced. Otherwise, they start rolling. So this is the dorsal fin here. Pelvic, also known as ventral fins, help the fish stay stationary. They also aid in turning and stopping. Some fish have a modified pelvic fin that help fulfill specific niches, such as tactile feelers. Some gouramis have that. Suction to stick to surfaces. Gobies will have that. Breeding claspers. Some cichlids and other fish will also have that. Pectoral fins help fish through propulsion, swimming in place. Think of doggy paddling in humans. They're kind of swimming in place, right? Steering / direction, coming to a stop, and even stability. And here we have the anal fin. The anal fin will aid fish in stability by preventing the fish from rolling, which is very similar to the dorsal fin in that aspect. And fish such as live-bearing fish, which are ovoviviparous or viviparous, where the males use, ovoviviparous or, viviparous. Okay, I said it right. Where the males use their modified anal fin, also known as the gonopodium, for internal fertilization. So you can see here, let me go ahead and get the pen. So we have the dorsal fin here. This is a male. You can see the dorsal fin. This is the dorsal fin. And we have a homocircle caudal fin here. It almost resembles the truncate. And then here we could see this is the ventral fin, or one of the ventral fins. There's another ventral fin on the other side of the fish. And then we also have, of course, we have the pectoral fins. We have one here, and then the other one's on the other side. And then this is the anal fin here. So this is the gonopodium I was talking about. This is actually a live-bearing fish. This is Phyllictes tico. And you can see that the anal fin on this fish is a modified anal fin. So it is a gonopodium. And the female here, you can't really see it too well, but her anal fin is more, it's kind of like what a traditional anal fin would look like. So it looks like this. It's kind of hard to see. It's behind the ventral fin, but it is there. Right? So how fish swim. So eels and fish in their larval stage, because larval stage fish kind of look like little, like little tadpoles kind of. They have that shape. So eels and fish in their larval stage move through the water primarily using their trunk. So the trunk is the section between their head and tail. So you can think of it as like the mid portion, which limits their speed and stability. But they have the greatest maneuverability. So eels, or anguilliforms, they have some of the best maneuverability because of this aspect. But this limits their speed and stability. So we got to keep that in mind because they're just moving, They're just using their trunk to undulate. So this kind of motion is called undulation. Salmon and trout use this type of motion. We're talking about subchrangiforms. So subchrangiforms essentially undulate their back half, and it's mostly utilized by salmon and trout. There's the subchrangiforms, and then there's chorangiforms. They use the posterior third of their bodies to swim, like mackerel here. Tuniforms are the fastest swimmers, but have the least amount of maneuverability. So when they turn, it's pretty bad. Like it takes a lot more for them to turn than it would, let's say, an eel, right? So how do fish combat these forces? So the slime coat. Fish have a coat of mucus over them that protect them from disease, but also help them reduce drag force by up to, some species can reduce it up to 65%. The streamlined shape, as we went over earlier, many fish have a streamlined body shape to help reduce friction and turbulent pressure resistance. Scales. Another method of drag reduction in fish are their scales. Scales help fish move smoothly in the water by reducing friction. They are also streamlined shaped. Swim bladder. Fish remain buoyant in the water with their swim bladder. Most ray fin fishes have a closed swim bladder chamber within their body, which allows them to regulate the gas inside. So when a fish needs to be at a specific depth, they can adjust the gas within their swim bladder to achieve neutral buoyancy within said depth. This allows them to conserve energy by allowing them to not have to constantly swim up or down. And that's it. Thank you for listening and watching, and I appreciate it.